In our previous lectures, we have derived various forms of interpolating polynomials to fit a given data which consists of an abscissa and the corresponding ordinate at n plus 1 points. Now, we derived the various forms in the sense we have Lagrange interpolation, divided difference interpolation, and if it is a equi-space data, we have the Newton's formulas of backward forward formulas. And if we add for this data one more item like the slope of the function that is representing the given data, then we can have a different type of polynomial altogether. So, let us now consider data of this particular form. The data that is given to us shall be the abscissas that we take it as xi, this is your x naught, x1, so on xn. Then we have the ordinates given to us as f0, f1, fn. Now, this was the data that we considered earlier. Let us now add to this slope at these points also. So, let us also consider the case when we have slopes also at this, which we shall write it as f prime at 0, f prime at 1, so on f prime at n. Now, what type of interpolating polynomial can we derive for this particular data? Now, if you look at this number of ordinates that we have n plus 1 values of these ordinates. Now, if you consider simply the data xi fi, that is this data, then we were able to write down a polynomial of degree less than or equal to n, which fits this data exactly. Now, we have added to it n plus 1 more values, these are again n plus more values. Therefore, this implies that we have a total of 2 n plus 2 values that are available to us. Therefore, in this data we have 2 n plus 2 values available to us. Hence, this implies that we can fit a polynomial of degree less than or equal to 2 n plus 1 for this data. Therefore, a polynomial of degree less than or equal to 2 n plus 1 can be fitted. And the polynomial which does this job, we shall call it as a Hermite interpolation. So, we shall call this as Hermite interpolation. That means, we want to construct a polynomial p such that p at xi is equal to f at xi and p prime at xi is f prime at xi for I is equal to 0, 1, so on n. Now, we shall follow the procedure that we have adopted in deriving the Lagrange interpolation. Now, the interpolating polynomial must be a linear combination of these ordinates and these slopes also. That means, I must be able to write down the polynomial p x as equal to summation of I is equal to 0 to n sum a I x f of x I plus summation 0 to n b I x f prime at x I. So, the polynomial should be a linear combination of these ordinates n plus 1 ordinates and n plus 1 slopes. Now, since this polynomial is of degree less than or equal to 2 n plus 1, a I x and b x must be polynomials of degree 2 n plus 1. These are polynomials of degree 2 n plus 1. Since this polynomial should fit this data exactly, we can find out the conditions under which this approximation is possible for us. So, let us substitute xi here and see what we would get the conditions on ai and bi. Some xj, let us put xj, I is equal to 0 to n, ai xj into f x I plus summation I is 0 to n b I x j plus into f prime of x I. Now, this should be identically equal to, this is p 2 n plus 1 suffix p 2 n plus 1. This should be identically be equal to f of x j, that is your p of x j is equal to f of x j, that is the data given to us. Now, if this is to be true, it should be identically. Now, all this b I x j must be 0 because there is no derivative here. So, let us put it here in two ways, b I x j is equal to 0 for all I j, b I x j must be equal to 0 for all I j. You write it in two columns. So, we shall fill up the remaining data over here. Now, let us look at a I x j, this should be equal to f x j, therefore, all of them would be 0 except when the both suffixes are same. So, you will have here a I x I is equal to 1, a x j is equal to 1 for I is equal to j is equal to 0 for I not equal to j. Then this will give us simply 1 into f of x j. So, it will be identically equal to this. Now, we shall fill up here, I will just leave some space over here. Let us differentiate this and set x j here. So, I am differentiating this particular polynomial and then do it. So, it will give us derivative of a I and here it will give derivative of b I. These are constants. So, only derivative of a I and b I will come. So, that we can write it as summation I is equal to 0 to n a I prime x j f x I plus summation I is 0 to n b I prime x j f prime at x I. Now, you can see that this should be identically equal to f prime of x j, because the interpolation condition is p dash x j is equal to f prime of x j. Therefore, this should be identically equal to this. Therefore, this implies that there cannot be any ordinates here, that means this a I prime x j will be 0 for all I j. So, that means I can now write here a prime I x j is equal to 0 for all I j, whether it is equal or not equal. In all the cases, the value of a prime x j will be equal to 0 and b prime x j will be equal to 1 when I is equal to j, and it will be 0 for I not equal to j, because this should produce f prime at x j. Therefore, we will have here b I prime x j is equal to 1 for I is equal to j is equal to 0 for I not equal to j. Now, we need to construct now a I and b I just as we have done in the Lagrange interpolation by looking at the property of a I and its derivative, b I and its derivative. Now, we remember that a I and b I are polynomials of degree 2 n plus 1. So, what we will do it, we shall take advantage of the Lagrange fundamental polynomials which are polynomials of degree n. So, if I consider L I square, this will be polynomial of degree 2 n, polynomials of degree 2 n, and this satisfies our properties that L I x j is equal to 1 for I is equal to j, L I x j is equal to 0 for, we know this property that L I x j is equal to 0 for I not equal to j is equal to 1 for I equal to j. Because of this property which is inbuilt for a construction of this, I shall use this L I square Lagrange fundamental polynomials in building this a I and b I. So, what I would do, since L I square is a polynomial of degree 2 n and a I b I are only polynomials of degree 2n plus 1, I need to multiply this only by a linear polynomial. That means, we shall assume that let a x is equal to suffix I, some suffix I you put it, a I plus b I into x minus x I L I square x, and b I x is equal to some c I d I x minus x I L I square x. Now, L I square is a polynomial of degree 2n. I am now multiplying this by a linear polynomial of the special form, which I have taken it in this particular form, because it is easy for us to find the constants in that case. Now, this is a polynomial of degree 2n plus 1, and this is also a polynomial of degree 2n plus 1. If we are able to find uniquely a I, b I, c I, d I from the data that we have, then we have what we have written the formula or the is correct. So, let us try to find that one. Let us look at, let us just put this conditions over here. We shall now determine the parameters a I, b I, c I and d I using the conditions on a I and b I, which we have obtained earlier as this, where a I x j is equal to 1 for I is equal to j, it is 0 for I not equal to j. Similarly, a I prime x j is equal to 0 for all I and j, and similarly the conditions on b I. We shall apply these conditions one after the other to determine the constants a I, b I, c I and d I. Let us first of all substitute x I in a I x. So, if I substitute x is equal to x I get here a I plus 0, this is 0, then I get L I x I is 1, therefore, L I x I square is equal to 1, and this should be equal to 1. A I is equal to 1 for all I. Now, we have determined the one of the parameters a I in this a capital A I. Now, let us differentiate a I, therefore, I will get a I prime of x is equal to, is a product of two functions. So, let us write this product as a I plus b I into x minus x I, derivative of this is 2 times L I x L I prime x plus the derivative of this gives us simply b I into L I squared of x. Now, we have the condition that a I prime x j is equal to 0 for all I j. Let us now substitute and see here. If I put a I prime x I here, I would get here is a I plus x is equal to x I, that is 0, then I will have here 2 times L I x I is equal to 1, I will have L I prime of x I plus L I x I is equal to 1, therefore, I will have here b I into 1, and the value of a I prime x I is equal to 0. That is a condition that we have here, that a I prime x j is equal to 0 for all I and j. Therefore, I can determine b I from here, therefore, I will have b I is equal to minus 2 times a I into L I prime of x I, but a I is equal to 1, therefore, I will get is 2 times L I prime of x I. Now, similarly, we shall apply the conditions on b I to determine the constant c I and d I. Now, let us substitute x is equal to x I in b I of x. So, if I put b I x I, that gives me, I am now substituting here in this the I am substituting x is equal to x I in this. So, let us keep this slide here, this is c I plus 0 L I squared of x I, and this is equal to 1, therefore, this gives us c I into 1, but this is equal to 0, this is equal to 0. Therefore, we get c I is equal to 0 for all I. Then let us differentiate B I x. Let us differentiate B I x from here. So, I will have here B I prime of x is equal to C I plus d I into x minus x I. Derivative of L I square is 2 times L I x L I prime of x plus derivative of the first one gives us d I into L I squared of x. Now, we use the condition that B I prime x I is equal to 1. So, if I put B I prime of x I here, I get here C I plus this is 0, that is 2 times L I x I L I prime of x I plus d I into 1. Now, B I prime of x I is equal to 1, therefore, this is equal to 1. Now, C I is equal to 0, therefore, this bracket goes off and we are simply d I. Therefore, we obtain d I is equal to 1 for all I. Now, we have determined all the 4 constants. So, we can now substitute in the expression for A I x and B I x, that is this expression A I x and this. Let us substitute it and see what we get. We get A I x is equal to A 1 minus 2 times x minus x I into L I prime of x I into L I squared of x. Now, this we have obtained it because we have got here A I is equal to 1 and we have obtained B I is equal to minus 2 times A I L I prime of dash x I. So, we have substituted for B I and this is x minus x I over here. Therefore, this is the expression in the brackets for A I x and outside the bracket we have L I square x. Similarly, we get for B I x, this is equal to, now C naught is 0 and d I is equal to 1, therefore, I simply get x minus x I into L I square of x. And therefore, for the required polynomial P x is equal to summation of I is equal to 0 to n A I x f of x I plus summation I is equal to 0 to n B I x of f prime of x I. We call this as the Hermite interpolating polynomial. We call this as the Hermite interpolating polynomial. Which is of degree less than or equal to 2n plus 1. Now, to compute this interpolating polynomial, we need to determine L I x, I need to determine L I prime, then substitute the values over here, determine my A x B I x from here, sum them up, simplify it to finally arrive at the polynomial of degree 2n plus 1 or less than 2n plus 1, and that represents the interpolating polynomial which fits exactly the given data. Now, let us take an example on this. Let me write the example. Now, construct an interpolating polynomial that fits the data x. Let us take only 2 points, f x is 2 values, 2 ordinates, and the slopes f prime x is 4 and 32. Now, we need to first of all write down our Lagrange fundamental polynomials Lix. There are only 2 data points, therefore, we will have L0x is equal to x minus x1 upon x0 minus x1. That is x minus 2 divided by 1 minus 2, that is minus 1, which is your 2 minus x. And we need the derivative also, let us differentiate it, L0 of x also, let us write on x also, that is equal to minus 1. Here it is a linear polynomial, therefore, derivative is a constant, otherwise this would not be a constant. If we take more data points, it will be a function of x. Now, let us write down L1x. This is x minus x naught divided by x1 minus x naught, that is x minus 1 divided by 1, that is your x minus 1. We need its derivative also, let us differentiate it, this is equal to 1. Now, we need to find the quantities a naught a1, b naught b1 to use this particular expression. Now, we set I is equal to 0 in this to get a0 x. Now, we shall say set I is equal to 0 in a I x. Then we get a0 x is equal to, now we are setting I is equal to 0, therefore, I will get here x naught, this is L0 prime x 0, this is L0 square x. So, I will get here 1 minus 2 x minus x 0 L0 prime x 0 into L0 square of x. Now, I will substitute the values of L0 prime x 0 is minus 1, L0 x is equal to 2 minus x. Therefore, I will get here is 1, this is negative sign. So, I will write it as plus 2, x minus x naught is 1, L0 square is 2 minus x whole square. We can simplify and write this as 2x minus 1 into 2 minus x whole square. Now, set I is equal to 1 in a I x. We get, I am setting I is equal to 1. So, I will have here x 1 L 1 prime x 1 L 1 square x. Therefore, I will get here a 1 x is 1 minus 2 times x minus x 1 L 1 prime x 1 into L 1 square of x. Now, x 1 is equal to 2, L 1 prime of x 1 is 1 and L 1 x is x minus 1. Therefore, I get here 1 minus 2 into x minus 2, L 1 prime of x 1 is 1. So, I will have this as 1 and L 1 square of x is x minus 1 whole square, that is x minus 1 whole square. Therefore, this I will get it as 4 plus 1 5 minus 2 x into x minus 1 whole square. Now, set I is equal to 0 in b I x. Therefore, I will get b 0 x is equal to x minus x naught into L 0 square x. Again, our L 0 is 2 minus x. Therefore, this will simply give us x minus 1 into 2 minus x whole square. Now, set again I is equal to 1 in b I x. Therefore, I will get b 1 is x minus x 1 L 1 square x. Therefore, I get b 1 x is x minus x 1 L 1 square of x. X 1 is 2. Therefore, I get here I get x 1 is 2 and we have got here L 1 x is x minus 1. Therefore, this is equal to x minus 1 whole square. Now, we got these 4 quantities and which we can substitute now in P x to get our polynomial. Therefore, the required Hermite interpolating polynomial is P x is equal to a 0 x f of x naught plus a 1 x f of x 1 plus b 0 x f prime of x naught plus b 1 x f prime of x 1. Now, we can substitute the values that we have obtained earlier, that gives us 2 x minus 1 into 2 minus x whole square into 2 plus 5 minus 2 x into x minus 1 whole square into 17 plus x minus 1 into 2 minus x whole square into 4 plus x minus 2 into x minus 1 whole square into 32. Now, we can simplify it and we get the result as 8 x minus 6 into 2 minus x whole square plus 21 minus 2 x into x minus 1 whole square. Now, you can easily verify that this fits our data exactly. Now, before we proceed further, we should make some comments or a little word of caution on using the interpolating polynomials. If a large data is given, say n plus 1 points, we can construct a polynomial of degree less than or equal to n to fit the data. But the data that we have got is usually from an experiment or from some observations. Therefore, if you are given a say 4 place accuracy table, the last digit of this is always due to round off error, because you are rounding it off is there. Now, if you are constructing a polynomial of degree 99, say for the data given as 100 data is given, if you are constructing polynomial of degree 99, we are now using the multiplications of these ordinates by numbers which are the coefficients in the polynomial. Therefore, the round off error that is there in each data item gets multiplied and cumulatively the total round off error will be enormous, and no experiment you can give the result exactly. Therefore, it is not advised and it is not used to construct higher order degree interpolating polynomial, even though the data is very large. The only alternative would be to at the most go up to cubic or a 4th degree polynomial. Beyond that we do not go, and hence it is possible for us to break the data into blocks. Say for example, if you have got, suppose we have got a data of say at these 6 points, where let us write down this data. Suppose I have given the data as these 7 points are given. I know that I can construct the polynomial of degree 6. If it is slopes are given, we can construct a polynomial of degree 13, but what we are stating is in practice we should not use that. What will we use it? For example, I can break this into 2 blocks of these points. So, this contains 4 points, this contains 4 points continuously x 0 to x 3, this is your x 0 to x 3, this is x 3 to x 6. Then I construct interpolating polynomial on each of these blocks. So, construct interpolating polynomials on each of these blocks. Now, in this case they are cubic polynomials. In this case they are cubic polynomials. Then we shall call such interpolation as piecewise interpolation. So, we shall call this as piecewise interpolation. It has all the properties of the interpolating polynomial that we have discussed here, except that the entire data is being made into small blocks, and on each of them we are constructing a cubic polynomial. For example, 4 data points, if we are taking 3 data points, we will have here a quadratic, quadratic, quadratic. Therefore, we are going to write down the interpolating polynomial as something like, for example, here I would write this as Px is equal to some a1 x cubed plus b1 x squared plus c1 x plus d1 for x naught less than x less than x3, and I can put equal to, because we have taken the point in both, it is both of them are fitting exactly at x3, therefore, it is continuity at x3 is available for us. This is some a2 x cubed plus b2 x squared plus c2 x plus d2, x3 is less than x less than or equal to x6. Either put equal to here because both of them are going to be the same thing, that of course that p at x3 is equal to fx3. So, both of them would satisfy this. Therefore, in this way we can give for the entire data, we can say that for this first block this is the polynomial, second block this is the polynomial, third block this is the polynomial, and then use this piecewise interpolating polynomials for predicting the data values at any of the intermediate points. This is what we normally do in practice if you have a very huge data. Even though theoretically we can construct very high degree polynomial, but in practice we shall not be using it. Now, let us look at the second problem in this, that is your approximation. Now, we mentioned earlier that the problem of approximation is of two types. One type is that data is given to us, data is given, we know that it represents a function f x, it represents a function f x, but without actually constructing this function f x, we would like to write down an approximating polynomial or a function which approximates f x for this given data. Now, the problem is therefore to find an approximating function to f x without constructing f x. That means, we would like to construct the function without actually going through the process of interpolation. Now, the second is that we are given a function f x, here we are given f x, the problem is to approximate f x by a suitable function What is this function? It could be polynomials or orthogonal polynomials, that is they are functions of polynomials or in terms of orthogonal polynomials. So that the properties of the function given to us, which was a complicated function, can be studied through these polynomials, because when once we write it in terms of an orthogonal polynomial, we know all the properties of the orthogonal polynomial implied there, and we can use those properties to say about the behavior or any other property that we need of the given function f x. Now, if we want to construct these two, first of all we must guarantee ourselves that such a representation in terms of polynomials or in terms of orthogonal polynomials is guaranteed for us, otherwise we are not sure whether what we are obtaining is correct or not. The answer for this is yes, we have a theorem called Weierstrass theorem, which states that if you have a continuous function over an interval a b, then we can always approximate it by a polynomial. So, that is known as Weierstrass theorem, which guarantees that what we are doing is correct and we will be able to get a unique polynomial from there. Let us define what is our Weierstrass theorem. So, we have a function which is continuous, belongs to the class of continuous functions over the interval a b. Then the theorem states, then given an epsilon greater than 0, there exists a number n which is a function of epsilon such that f x minus p n x is less than epsilon for all x contained in a b, where p n x is a polynomial of degree n, where this p n x is a polynomial of degree n. Therefore, the Weierstrass theorem guarantees that we can approximate a continuous function by a polynomial of degree n. So, we will take this assumption that it is possible. Then how to construct this particular function using this particular the definition that f x minus p n x should be less than epsilon. Now, the problem is therefore is to how to find p n x. What we do is we take p n x in terms of some function f, that is polynomial or orthogonal polynomials, whatever that we given here. Therefore, f x will be approximating polynomial in terms of the variable x, and we introduce some constants c naught, c 1, c 2, c n, c naught to c n. That means, what we are essentially writing here is some c naught phi naught of x plus c 1 phi 1 of x plus so on c n phi n x. Phi I x are the known functions, these phi I x are the known functions or the known functions. Phi x are the known functions. For example, they can be taken as polynomials. I can simply take it as phi x is equal to x to the power of I. I can take phi x is equal to x to the power of I. That means, phi 0 is 1, phi 1 is x, phi 2 is x square. That means, what I am really writing here is c naught plus c 1 x plus c 2 x squared plus so on c n x to the power of n. That is simply a polynomial. That is what we have this. Or I can take phi I x as orthogonal polynomial. Orthogonal polynomials, which are orthogonal with respect to a weight function, orthogonal with respect to sorry, with respect to a weight function. Now, what we are really talking of is the Legendre polynomials and the Chebyshev polynomials. the Legendre polynomials are orthogonal with respect to 1, weight function is 1, whereas the Chebyshev polynomials are orthogonal with respect to weight function 1 upon under root 1 minus x square. That will come later on, but we are just saying why we are introducing a w x here, because these orthogonal polynomials have a weight function over which they are orthogonal. Now further, the phi x could be any other function which represents your experiment properly. For example, if in an experiment the solution of the variable is in the form of sine or a cosine wave, we can write down this as, for example, I could simply write this as some a plus b sin x. I can take an approximation for this as a plus b sin x, but I must be able to determine the parameters a and b. Now therefore these C1, C2, Ci, these Ci are parameters to be determined, parameters to be determined. Now we must give the rule under which these parameters can be determined. For that we shall consider the error that is coming from here. So we will take the error here. Therefore the error, let us write down E of f c, c is the vector of this C0, C1, C2, C3, and we will take this as norm of f x minus C0 phi 0 x Cn phi n x, where this is a well defined norm. It is a one of the norms that we know, it is a well defined norm. Now therefore the problem reduces to how do you find this Ci. Therefore the problem is to find Ci, to find Ci such that the error is minimized, the error should be smallest, to find Ci such that error norm is minimized. That particular approximation for which error is minimized, that means that particular approximation, this approximation for which this error is minimized shall be called as the best approximation. So this shall be called as the best approximations. Of course we should qualify it as with respect to that norm which we have used, with respect to that norm. Now we have specified how, what we mean by this error, what are the things that we have to do, we have to find Ci such that the error norm is minimized. Now the next step we shall define is what is norm. We have earlier given a number of definitions of norms, of which we shall use two of the norms. One norm that we shall use is the Euclidean norm, Euclidean norm. Now let us define what is this Euclidean norm. Let us suppose we are given a data, then we shall define this norm as norm of x is equal to summation of magnitude of xi square to the power of half. So we are taking the summation over the all the elements, magnitude of xi square whole to the power of half. However, if we are given a continuous function f x, then we define the norm of f x as is equal to integral of a to b w x f squared of x to the power of half, where w x is the weight function that we are talking of earlier, is the weight function and which is greater than 0. So we can use this definition of Euclidean norm to obtain the values of the constants that we have just now defined in the error. In this case we would get what is known as the least square approximation. We obtain the least squares approximation if I use this particular norm and determine the constants C I such that this norm is minimized. Now we use another norm which we shall call it as uniform norm. Uniform norm. Again, if you are given a data, I would define norm of x is equal to the largest element in magnitude maximum of xi of xi. And if you are given a continuous function, again if you are given a continuous function, then we define this as norm of f x is equal to maximum in the interval a to b of magnitude of f x. Now we use this either for the data discrete data that is given, or if we are given a continuous function. Now if I use this particular norm to determine the constants C I, then what I would get is known as the uniform approximation. We get uniform approximation in this case. Now in our next lecture we shall see that how we are actually apply this minimization problem, that is the minimization of the norm to get least square approximation, or minimize these norms to get the uniform approximation, and thereby construct a polynomial or a function in terms of the orthogonal polynomials which gives us the best approximation, Okay, thank you.